So we're now trying to finish off the last direction in our proof of a bunch of equivalence condition to the mutability. And from last time, we saw that we can actually have a character. So if G is immutable, then the reduced C-star algebra actually has a character on it. And we're trying to use that to build some kind of left invariant mean on G using some kind of Banach. But before we do that, we need one little technique, which is actually called the multiplicative domain technique. It's a really standard and neat way of doing things in operator algebra, and it's going to use some knowledge on the completely positive maps. So I know I have been using a lot of knowledge from operator algebra, for example, the A10, a bunch of C-star algebra stuff. But the multiplicative domain is not going to be in that course. So if there's any course on completely positive maps, you'll probably see that. But otherwise, it's a really neat technique. So if the good reference will be the Vern Paulsen's book on the completely bounded maps and completely positive maps. And we don't have a lot of topic course on that. So I'll just give a brief introduction to this technique in this video. And hopefully you enjoyed it and find it useful. So to show the multiplicative domain technique, let's start by considering some lemma. So first of all, I want to prove a little lemma. And it's probably also one of my favorites because as you already noticed, I really like these operator matrix idea. So let's just think about what happens when some kind of operator matrix is positive. So let's say H1 and H2, they're Hilbert space. And if I want to consider a 2x2 operator matrix, let's say, suppose I have identity on this entry, and then I have an A and A star, and then I have a B. So I treat this as, so this is one is from H1 direct sum H2 to H1 direct sum H2. So the A is going to be a bounded linear operator from H1 to H2. And so A star is from H2 to H1, and your B is from H2 to itself. And the identity, of course, is just the identity on the H1 space. So this one, you can treat it as a bounded linear operator on the H1 direct sum H2. Okay, so this is really from B of H1 direct sum H2. And so if this one is positive, so this one is positive, there's a really nice characterization. There's you only need to check A star. So A star will map from H2 to H1, then use A to map it back to H2. So you can compare with B. That has to be less than equal to B. Okay, so less than equal in terms of operator on understood as operator on the H2. All right, so to show that, this is really neat proof. So one direction is easy. So if you have this kind of inequality on the right, then what you can do is that you can break this 2x2 matrix using the following way. Well, you know, if I have say A and A star here, and if I just replace the B by A star, then this matrix is just the product of IA, this column matrix, multiplied by its conjugate, the row matrix. And whenever you have something like X star, doesn't really matter whether your X is a row matrix or a column matrix, as long as it's written in this form, it's always a positive operator. Okay, so this is clearly always positive. But the difference is that you also need to add the difference. So here you have a B minus A star, okay, and you have 0, 0, 0 here. And when your B minus A star, well, this matrix, well, a bunch of entries are just 0, so it's a 0. You can treat it as a 0 direct sum and copy of a B minus A star. And this one is positive if B minus A star is a positive operator on the H2. Okay, so if you add two positive operator, they are still positive, so you get this operator matrix is positive. The other direction is basically built upon the kind of the same idea. So suppose not. So suppose I don't have the inequality on the right, then basically I can find some vector inside the H2. Let's call it eta. So that when I tried it on A star eta in the product with eta, I got something strictly bigger than B eta. And by the way, if your operator matrix is positive, it has to be self-adjoint. So this B really have to be self-adjoint. So B eta inner product with eta is a real number. So this inequality has to make sense. All right, so you kind of use the same idea. So you want to build some vector where when you test it on this 2x2 operator matrix, it will give you something that's negative. So it's no longer it's contradiction to that matrix being positive. And this decomposition really tells you kind of what kind of thing you need to choose. All right, so let's do this. So let's pick the following vector. So let's pick, so I take a negative A star of eta, which A star will map eta to H1, so it belongs to H1. And then I put eta. So I treat this as a vector inside H1 direct sum H2. All right, so what you can see is that if you put it on this matrix, A, if I have a A star here, and if I test it on this vector, okay, so yeah, in fact, if you just expand the left-hand side, you'll see that because everything just cancels out, you will get something 0. So in particular, if I just test it on here, I do have a 0 here, okay? So this is, if you try it, that's going to be the 0 vector. All right, so but you also, if you want to test it, this matrix 0, 0, 0, B minus A star on this vector, what you get is, well, because a bunch of things are just 0, so when you try to do the inner product, you wouldn't end up with the BAA star of eta, which is strictly less than 0, okay? Well, because of that, you add them up, okay? So, and everything is linear, so you basically show that when you test your 2x2 matrix on this particular vector, you get something less than 0. So that just implies that A star, B is not positive, okay? Because it's not positive on some vector, all right? So we need to prove another little lemma, so let's write it here. So I also want to do the following. So if I have a 2x2 operator, but I have a 0 on the diagonal, on the upper left corner, if that's positive, okay, the same thing here. The A and B, they're both on A is from H1 to H2, B is from H2 to H2. But on the left corner, if I don't have an identity, but I have a 0, then I have that A has to be equal to 0. Okay, the only chance is that this is basically just a bunch of zeros, but only B, and of course B has to be positive. All right. So to prove that, okay, that's actually quite simple. So if you just take any, so for every, say, eta 1, eta 2 inside H1 direct sum H2, if you just consider this matrix, so you have A star, A, B tested on eta 1, eta 2, and then you in the product with the same vector, what you do is that this is essentially just so you do the, let me write it out. You have the A star eta 2 in the product with eta 1, and then you have an A of eta 1 in the product with eta 2, and then you have a B eta 2, eta 2. And the first two, each one of them is the conjugate of the other, so I can write as twice the real part of the A eta 1 with eta 2 plus B times eta 2, eta 2. And the nice thing is that if I want to scale this eta 1 by any scalar t, so if t is in real, then I basically only scale the first part, okay? So this t only multiplies in here, the eta 1 part. It doesn't affect the second part, the b eta 2 part. So if I do that, well, as you can see, as long as a eta 1, so if a eta 1 is non-zero, then you can always pick some eta 2 so that this inner product, this real part of this inner product is non-zero. But then you can pick some t so that there exists some t inside R, so that whatever you have here is going to be strictly less than 0. Okay, you just scale your t big enough because it doesn't affect the second part. This star is going to be a linear function in terms of t. As long as your slope is non-zero, it's going to go to negative eventually. All right, so this is going to be a contradiction. Okay, so contradiction. So this finish the proof of this little lemma.